Welcome to Advanced Quantum Chemistry and my third lecture on correlated wave function methods. In this lecture I will talk about Møller-Plesset perturbation theory. Møller-Plesset perturbation theory is the application of normal perturbation theory to the problem of electron correlation. It was first derived by Møller and Plesset in 1934, but was not started to be used routinely in quantum chemical calculations before around 1976, where there was a paper by John Popel and it was implemented in the Gaussian program. Like always in perturbation theory, one starts out with partitioning the Hamiltonian in an unperturbed Hamiltonian and a perturbation. And different methods for the treatment of electron correlation, they distinguish them by how this partitioning is done. In Møller-Plesset perturbation theory, the zeroth-order Hamiltonian, the unperturbed Hamiltonian, is made as the sum of the Fock operators. So this is actually the operator which in my lectures on Hartree-Fock theory I call the Hartree-Fock Hamiltonian. And the perturbation Hamiltonian, the perturbation operator, is then just the difference of the total Hamiltonian minus this zeroth-order Hamiltonian. So the difference between the total Hamiltonian and what I call the Hartree-Fock Hamiltonian. The co-Hamiltonian in the full Hamiltonian and the Hartree-Fock Hamiltonian is the same. Therefore, taking the difference, it disappears. So what is left is the difference in the operators describing the electron-electron interaction, electron-electron repulsion. And in the full Hamiltonian, of course, we have the normal Coulomb law repulsion operator 1 over the distance between the electrons, whereas in the Hartree-Fock Hamiltonian we had replaced that by an average potential where we have the Coulomb and the exchange operator. So the perturbation operator is actually just the difference between these two ways of treating electron-electron interaction, the correct one minus this averaged one. And that means that this perturbation operator is actually the deviation from the average here. And therefore it's called the fluctuation potential, because it's the idea of that the real electron-electron interaction is sort of fluctuating around the average. So we partition the Hamiltonian, this zeroth-order and first-order Hamiltonian, and then one writes up, like always in perturbation theory, an expansion of the exact wave function in a series with the zeroth-order wave function, first-order correction, second-order correction, and so forth, and correspondingly for the energies. And one inserts it all in the Schrödinger equation, and then one separates equations of different order. And here on the next slide I have the zeroth-order equation written up, where we have this zeroth-order Hamiltonian, which, as said, is what I used to call the Hartree-Fock Hamiltonian. We have a zeroth-order wave function, and we have the zeroth-order energies. Now, one should remember from what, as we discussed in the case of Hartree-Fock theory, that all the Slater determinants which are made from molecular spin orbitals, meaning all the Slater determinants which are made from the spin orbitals which are eigenfunctions to the Fock operators, they are eigenfunctions of this Hartree-Fock Hamiltonian. So the functions which fulfill this zeroth-order wave function are just all our Slater determinants made from the spin orbitals which are the eigenfunctions of the Fock operators entering this zeroth-order Hamiltonian. And the eigenfunctions, the eigenvalues are, as we also already saw in the chapter about Hartree-Fock theory, are just the sum of the orbital energies. So if you're going for the ground state, if you want to do Møller-Plesset perturbation theory for the ground state energy, then of course the zeroth-order energy, the zeroth-order wave function, which has the lowest energy, is going to be our Hartree-Fock wave function. So our zeroth-order wave function is the Hartree-Fock wave function, and the zeroth-order energy, well, we can write it up as the expectation value of our wave function and the zeroth-order Hamiltonian. That is just the sum of the orbital energies. Now the first-order energy correction, for perturbation theory, we always know that the first-order energy correction is the expectation value with our zeroth-order wave function, and we chose to go for the ground state. So that's our Hartree-Fock wave function and the first order Hamiltonian. Now if you insert now the first order Hamiltonian, which was the difference between the real electron-electron repulsion operator and the sum of our Coulomb and exchange operators, we get those two integrals. And using the Slater-Condon rules, this is a 2-electron operator, whereas those are actually effective 1-electron operators. We can evaluate this. So the first one gives just the sum over this Coulomb minus exchange integrals, like always in Slater-Condon rules. Whereas here, this being 1-electron operators, we get a sum over what looks in the first place as 1-electron integrals. But of course we should remember that the Coulomb as well as the exchange operator actually include an integration over electron 2. So in inserting that, it turns out to be that of course they are again 2-electron integrals. And they're actually the same integrals as we had here, but here is 1/2 and here's minus, so in total we get minus 1/2 this sum over Coulomb exchange integral. If you go back to the expression for the Hartree-Fock energy, you will see that apart from the minus sign, this is precisely the average electron-electron interaction. So our first order energy correction is minus the electron-electron interaction. Now if you now add the zeroth order energy plus the first order energy together, the first order energy correction together to get a first order energy, so we have the expectation value of the Hartree-Fock Hamiltonian with the Hartree-Fock wave function plus the expectation value of this first order fluctuation potential with the Hartree-Fock wave function. Obviously we can combine those two integrals into one. So we get the zeroth order plus the first order Hamiltonian there. That's together is the full Hamiltonian. So we end up with having the expectation value of the Hartree-Fock wave function with the full Hamiltonian of our system. And that of course we know is just the Hartree-Fock energy. So what we learn here is in this Møller-Plesset perturbation theory way of looking at it, the Hartree-Fock energy is actually a first order energy. Because the zeroth order energy, that's just the sum over the orbital energies, which you should remember in double counts the electron-electron interaction. And this first order energy correction repairs that because it was minus once the electron-electron interaction. So twice the electron-electron interaction minus 1 the electron-electron interaction gives us only one times the electron-electron interaction, so we get the Hartree-Fock energy. So the big conclusion of the paper by Møller and Plesset from 1934 actually was that a correction to the Hartree-Fock energy is not going to come in first order, but only first in second order we get a correction to the Hartree-Fock energy. Meaning the Hartree-Fock energy is correct to first order. Now here's the expression, the normal perturbation theory expression for second order energy correction, where we have here twice the first order Hamiltonian, we have our zeroth order wave function for the ground state, and then we have all the other, we sum over all the other zeroth order wave functions. And remember that all our zeroth order wave functions, they're just the Slater determinants made from our spin orbitals. And then the question, of course, is which of these Slater determinants can contribute here? And we have single excited, double excited, triple excited, and so forth. Now, single excited, well, by now you should know that a matrix element of the Hamiltonian and Hartree-Fock and the single excited are 0 because of Prion's theorem. Now here we don't have the full Hamiltonian, we only have this first order correction, but if one looks at it and evaluates this matrix element, it turns out to be actually to be the same. So the zeroth order, the single excited determinants are not going to contribute because of Prion's theorem. Double excited determinants, well, they can obviously contribute according to Slater-Condon rules, but more than doubly excited cannot contribute because then we have again a difference in more than 2 spin orbitals between Hartree-Fock here and whatever determinant we have there. So the only determinants which can contribute to this second order energy correction are actually double excited determinants. And this is our second order energy correction. Then, remember in the denominator we have zeroth order energies, the zeroth order energy of our Zeroth-order wave function and the Zeroth-order energy of these other Zeroth-order wave function, which are double excited determinants. Well, let's look at that a bit more in detail. So we have a matrix element between Hartree-Fock, this first order correction, this fluctuation potential, and the double excited determinant. And since there's a difference in two spin orbitals between the two determinants, because I is replaced by A and J is replaced by B, we only get one set of Coulomb minus exchange integrals, precisely those according to Slater-Conner rules. Now all our Zeroth-order energies, remember that all the Zeroth-order energies are sum of orbital energies. So E0, that is just the sum of all the occupied orbitals, which we have occupied in the Hartree-Fock determinant. And the Zeroth energy of this double excited determinant, that's just the sum of the orbital energies of all the orbitals which are included in this double excited determinant. Well, since it is a double excited determinant, that's the occupied orbitals, k again, but not I and j, because I and j was replaced by a and b, so it's this sum without I and j, and in addition we get epsilon a and b. Now if you take the difference between this sum of orbital energies and that sum of orbital energies, obviously here we are missing I and j, and here we're missing a and b, so we actually could just get the difference between those four orbital energies, between the two occupieds minus the two virtual ones. And at the end then, our expression for the second order energy correction in Møller-Plesset perturbation theory is this. We have the square of these Coulomb minus exchange two electron integrals divided by the difference of the orbital energies. And what is called the MP2 energy is then the sum of the zeroth order energy, the first order energy correction, the second order energy correction. So this is the sum of the Hartree-Fock energy plus this second order energy correction. And this method, Møller-Plesset perturbation theory second order, is actually the cheapest method for calculating a correction to the Hartree-Fock energy. It only includes double excited determinants, as you would have in, for example, configuration interaction doubles, CI doubles. But in contrast to CI doubles, in CI doubles you have to solve an eigenvalue problem because you have to determine the coefficients. Whereas here we have this fixed expression. There are no coefficients which we have to determine by solving an eigenvalue problem. We just have to evaluate the integrals and divide them by orbital energies, and we're done. So this is the cheapest way of getting a correction to the Hartree-Fock energy. Now that's for the ground state, Hartree-Fock ground state. There are also methods based on Møller-Plesset perturbation theory through second order for the calculation of other properties, which we will discuss later on. These properties, like for example electronic excitation energies or polarizabilities or NMR, chemical shift or coupling constancies. And one of these methods is called the second order polarization propagator, SOPPA or SOPA, which was originally developed at the University in Aarhus, but is now developed in my group, further developed in my group at the University of Copenhagen.